Good morning, everybody. Myself, Raghubir Singh, lecturer in civil engineering from Pandit Jagat Ram, Government Polytechnic College, Hoshiarpur. In the subject of fluid mechanics, today we are going to discuss on one of the topics of flow measurements. Now, let's have a look what are the different contents of today's lecture. We will start up with the definition of discharge. Then we will see what is flow measurement and what is its importance. Some of the technical terms related to orifice, notches and weirs. Then very important 4 hydraulic coefficients Cc, Cv, Cd and Cr. We will discuss in detail all these hydraulic coefficients. Then some of the devices for measuring rate of fluid flow. We have a lot of devices, amongst which we have orifice, mouthpiece, notches and weirs. And the last we will see what is single segment method, special method to calculate the discharge. So, starting with the definition of discharge. Discharge can be defined as the quantity of a fluid flowing per second through a section of a pipe or any channel. It is generally denoted by capital letter Q. Now, let us suppose if capital A is the cross sectional area of the pipe and capital V the average velocity of the liquid, then discharge Q is given by area into average velocity. So, very simple, Q is equal to A into V. Discharge is area into velocity, and as far as the units of discharge are concerned, it is measured in meter cube per second, or we can say in cusecks. Now, regarding flow measurements, the name of our today's topic. What is flow measurement and what is its importance? We all know that the rate of fluid flow or discharge through pipes, rivers, open channels, large tanks or reservoirs has to be measured. It is always required to measure the discharge through all these pipes, rivers, and this flow is measured mainly for the following purposes. Firstly, if we have to design various hydraulic structures like dams, barrages, etc., we need to have the discharge calculations. Then to plan for the optimum utilization of river valley projects. We all know we have a lot of river valley projects all over in India, and if it is planned for the optimum utilization of these projects, once again discharge calculations are required. Thirdly, to make an accurate assessment of the available water resources. We all know water resources are depleting day by day. So, it is very important to have the discharge calculations to make an accurate assessment of the available water resources. And lastly, to design the multi-purpose river valley projects, we again need discharge calculations. So, flow is generally measured in these different cases. It is always required to have the calculations of flow. Well, let us discuss some of the technical terms related to our today's topic. Very simple one, jet. What is a jet? A jet is a continuous stream of liquid that flows out of an orifice. It is a stream of a liquid. Then a very important term, the vena contracta. Vena contracta is that section of a jet where the cross-sectional area of the jet is minimum. Now, it will be clear from the coming diagram also. Repeating once again, the vena contracta is that section of a jet where the cross-sectional area of the jet is minimum. Now, this cross-section area is even less than that of orifice. And vena contracta, it's formed at a distance of 0.5 d from the wall of the tank. Now, what does it mean, all these calculations of vena contracta? Now, here is a diagram of a jet of water. It's a continuous stream of water. Regarding the vena contracta, if we have this wall of any tank and we have provided one hole here, which I call an orifice, an opening. Now, if a jet of water is coming out of this tank, you can very clearly observe that at this point the cross sectional area is minimum. So, this is what we call vena contracta, and it's again very clear, it is forming at a distance of 0.5 capital D from this wall of the tank. Now, what is this D? D is the diameter of this orifice, this opening. So, it will be at a distance of nearly half of this diameter. So, it must be clear from this diagram that what exactly the vena contracta is. Going again back to the same definition, it is that section of a jet where the cross sectional area of the jet is minimum. It is even less than that of orifice, and it is forming at a distance of 0.5 d from the wall of the tank. The third term, the velocity of approach. Now, this is the velocity with which the liquid is approaching the orifice in a tank. The velocity here in this tank, this is orifice. So, the velocity at which this water or jet is approaching this orifice is the velocity of approach. Now, this velocity of approach is negligible, very less as compared to the velocity at vena contracta. Since the cross sectional area is minimum at vena contracta, so it is understood the velocity will be maximum there. So, the velocity of approach, this is negligible as compared to the velocity at vena contracta. And to get the velocity at vena contracta, there is a formula, capital V is equal to under root 2gh, g the acceleration due to gravity, and this h is the depth of the liquid above the center of the orifice. This is important. H is the value, this is the depth of liquid above the center of the orifice. Now, I am interested to discuss some of the hydraulic coefficients which are very important as far as the flow measurements are concerned. There are mainly 4 hydraulic coefficients or orifice coefficients, I can say, related to discharge through an orifice. Now, these 4 coefficients are the coefficient of contraction Cc, the coefficient of velocity Cv, coefficient of discharge Cd, and coefficient of resistance Cr. We will see one by one all these coefficients. The first one is coefficient of contraction Cc. The coefficient of contraction is defined as the ratio of the area of jet at vena contracta, whatever is the area at vena contracta, to the area of the complete orifice. So, mathematically I can write coefficient of contraction Cc as the ratio of AC upon A. Now, what is AC here? AC is the area of jet at vena contracta, and A is the area of the orifice. Regarding the values of Cc, now the value of Cc varies from 0.61 to 0.69, and average value we often take for the calculation purpose, it is 0.64. Moving to the second coefficient, the coefficient of velocity denoted by Cv. The coefficient of velocity is defined as the ratio of the actual velocity, capital V, of the jet at vena contracta to the theoretical velocity of the jet, the actual velocity upon theoretical velocity. So, mathematically we can write coefficient of velocity CV as capital V upon under root 2gh. Now, this under root 2gh is the theoretical velocity, V the actual one, and h is the head under which the liquid flows out of orifice. Regarding the values of CV, the values varies from 0.95 to 0.99. So, this is the range of CV. The third coefficient is the coefficient of discharge, denoted by CD. Now, it may be defined as the ratio of the actual discharge to the theoretical discharge, or the ratio of the actual discharge from an orifice to the theoretical discharge from the orifice. Mathematically, again we can write CD, the coefficient of discharge, as capital Q, the actual discharge, upon small a into under root 2gh, the theoretical discharge, area into velocity. Regarding values, it varies from 0.61 to 0.65. The last coefficient, the coefficient of resistance. Now, this coefficient of resistance is defined as the ratio of the loss of the head in the orifice to the head of the liquid available at the exit of orifice. There are basically two definitions of this coefficient of resistance. The first one is the coefficient of resistance is defined as the loss of head in the orifice to the head of the liquid available at the exit of the orifice. Or there is a second definition of coefficient of resistance. It is the loss of kinetic energy in the orifice, Ke, upon the actual kinetic energy of the jet at vena contracta. So, with the help of both these two expressions, mathematical expressions, we can calculate the value of coefficient of resistance. There is a relationship between these coefficients. Now, let us see what is the relationship between CC, CV and CD. Now, we all know till now that coefficient of discharge CD is given by actual discharge upon theoretical discharge. CD is actual discharge upon theoretical discharge, and from the definition of discharge we know it is velocity into area. So, we can write this actual discharge as actual velocity into actual area, and we can write this theoretical discharge as theoretical velocity into theoretical area. So, just dividing these terms here, actual velocity upon theoretical velocity, it is separated here, and actual area upon theoretical area to the right hand side. And from the definitions of coefficients, actual velocity upon theoretical velocity, it is nothing but coefficient of velocity CV, whereas actual area upon theoretical area, it is nothing but the coefficient of contraction. So, we get a relationship between these three coefficients. This CD, coefficient of discharge, is equal to the CV multiplied by CC. So, this is the final expression for the relationship between these three constants. Now, moving right to the different type of devices for measuring discharge. We are interested to measure discharge. We have lot of devices, but in today's lecture we will discuss these four: the orifice, mouthpiece, notches and viers. We will see one by one. Regarding this venturi meter and orifice meter, we have already discussed these two devices in our previous lectures of Bernoulli's theorem, that how we calculate the discharge from venturi meter and orifice meter. So, in today's lecture I am interested to discuss these four devices, starting with the orifice. What is an orifice? An orifice is a small opening. It is a small opening on the side or it may be at the bottom of the tank. For what purpose? It is for measuring the discharge. Orifice is meant for measuring discharge. Now, important aspect regarding this orifice, the top edge of the orifice, this top edge of the orifice is always below the free surface of the liquid in the tank. As you can see in this tank, this is the free surface of the liquid, this is the top edge of the orifice, so it is below this free surface. It is always below the free surface. So, you can have a very clear idea from this tank that what is coming out of it. It is actually coming out of this orifice, an opening, small opening at the side of the tank. Something more regarding orifice, the functions of an orifice. As we have just discussed, an orifice is used to measure discharge of a liquid from the reservoir or from any tank. Secondly, orifice also helps us to find out the time required to empty a tank. Now, if this tank is full of water and we are interested to calculate how much time will it take to empty this tank. So, once again this orifice is very helpful. It will help to find out the time required to empty a tank. Thirdly, orifice can be used to find out the time required to fall liquid from a particular level to a desired level. Now, in this diagram, the water is falling from this level to this level. Now, if I am interested to calculate how much time will it take to get water from this level to this level, once again I can use this orifice to calculate the time taken by the water to move from this level at the orifice level to this floor level. So, once again orifice is very helpful here. Now, we have different type of orifices. There is a classification of orifice according to its size, according to its shape. According to size, we have small orifice and large orifice. According to shape, we have different geometrical shapes of orifices, rectangular one, circular one, triangular shape or square shape. We have a lot of shapes. According to the shape of the edge of the orifice, sometimes the edge is sharp, so it is sharp edged orifice. Sometimes it is blunt, it is bell mouthed orifice, or it is round cornered, it is not sharp. And fourthly, according to the nature of discharge, we have a condition of free discharging orifice, or we may have a condition of submerged orifice. So, this is the classification according to the nature of discharge. And the second one, the submerged one, is once again it is of two types. It may be fully submerged orifice or it may be partially submerged orifice. So, you have seen we can classify this orifice according to the shape, according to size, shape, then the shape of the edge, and maybe according to the nature of discharge. Now, to calculate the discharge through an orifice, now if this is a tank and here is the opening of at the side of the tank, or in other words an orifice is provided here, this is the head edge. So, considering a small one, now I have taken a combination of orifice. From the size I have taken the small one, from the shape rectangular one, from the edge the sharp edged free discharging orifice. The classification which we have just studied, we can combine the different properties of orifice and we can have this special orifice, smaller one, rectangular one. As you can see from the section, it is rectangular in shape, having a width of b and depth d. It is sharp edged, as you can see here, it is very sharp edged orifice, and it is a free discharging orifice. Now, to calculate the discharge through this orifice, we can see here that an orifice is called a small orifice if the head of the liquid is more than 5 times the depth of the orifice. Now, if this is the depth of orifice and this is the head of the liquid, if this head is 5 times greater than this depth of the orifice, then it is a small orifice, the definition of small orifice. Secondly, the velocity in the entire cross section of the jet is considered to be constant in the case of small orifice. We often see or assume that this velocity v, it is constant in the case of especially the small orifice, not in the case of large one. So, we consider the velocity as constant. And to get the value of discharge through this orifice, if a small a is the cross sectional area of orifice, h the height, b the width, d the depth, and cd the coefficient of discharge, then finally using this formula we can calculate the discharge through an orifice which is small, rectangular, sharp edged and free flowing. So, Q is equal to CD into A into under root 2GH. So, this is the final formula for calculating the discharge through an orifice. The second type of device to calculate discharge is mouthpiece. Now, how it is different from orifice? Now, orifice is a small opening, whereas mouthpiece is a short length of a pipe. As you can see here, this is a mouthpiece. It's actually attachment. It can be attached to any tank, and this piece of pipe, I can say it is mouthpiece. It's a short length of pipe, not too long, just 2 to 3 times its diameter, and it is connected to an orifice. Now, this is very important here. We connect this mouthpiece to the orifice, and mouthpieces are again used to increase the amount of discharge of liquid. Suppose we want in a particular tank to increase the amount of discharge coming out of it, we can use the mouthpiece. And thirdly, the diameter at the exit end of the mouthpiece here, this dia, it is known as the diameter of the mouthpiece. Repeating once again, what is the diameter of mouthpiece? The diameter at the exit end of the mouthpiece is known as the diameter of the mouthpiece. Regarding classification of it, once again, we have different types of mouthpieces. Firstly, according to the position of the mouthpiece, it may be internal one or external one, internal mouthpiece or external mouthpiece. According to the shape, a mouthpiece may be cylindrical, it may be convergent mouthpiece, or it may be convergent divergent mouthpiece. We have 3 varieties of mouthpieces according to shape. According to the nature of discharge, it may be running full or running free. Now, I will take a special combination, the external mouthpiece, cylindrical in shape, and as you can see from this diagram also, this mouthpiece is coming exterior to this tank, that's why it's called the external mouthpiece, and since it is cylindrical in shape, so that's why I'm calling it as external cylindrical mouthpiece. So, a cylindrical mouthpiece is a short pipe having a uniform diameter. As you can see from here to here, the diameter is uniform, and a mouthpiece projecting outside the body of the tank is called external cylindrical mouthpiece. Now, to calculate the discharge through this particular mouthpiece, what I can do, now consider this tank with an external mouthpiece as we have just seen. The jet of the liquid entering the mouthpiece forms vena contracta at CC. You can see a section CC here and the velocity VC here. This is the section of vena contracta. Now, let small a is the area of the mouthpiece, V is the velocity of the liquid at outlet, AC is the area of flow at the vena contracta. AC is the area here, and VC is the velocity of the liquid at vena contracta. To calculate the discharge through this particular mouthpiece, if H is the height of the liquid, small w the specific weight of the liquid, and Cc the coefficient of contraction, which we often take as 0.855, discharge can be calculated by applying this formula Q is equal to Cc into A into under root 2gh. So, this is the formula to calculate discharge through an external cylindrical mouthpiece, the one case of mouthpiece. Coming to the second one, I will take the different example. It will be internal cylindrical mouthpiece and with an special condition running free. Firstly, running free. It is an internal mouthpiece. An internal mouthpiece is a short cylindrical tube attached to the orifice extending inside the tank. As you can see here, it is extending inside the tank. When the length of the tube is equal to its diameter, repeating once again, when the length of the tube, this tube, it is equal to this diameter, in such cases the jet of the liquid comes out without touching the sides of the mouthpiece. You can see this gap here and here. These gaps are showing that this is the running free condition. This condition is called running free condition when the length of this mouthpiece is equal to the diameter of it, and the liquid coming out of it, it is not touching the sides of the mouthpiece. So, in this case, I can have different formula. Q is equal to Cd into A into under root 2gh, and I often take the value of Cd as 0.5. Rest of the terms are same, which we have already discussed: A, AC, Vc and H. Now, there is a second condition of running full. The previous condition, it was running free, the liquid is not touching the sides, whereas in this case running full, when the length of the tube is about 3 times its diameter. Now, this is different. This length is extended now. If the length is 3 times the diameter of this mouthpiece, the jet of the liquid coming out of it, it is equal to the diameter of this mouthpiece. Now, this water is touching the sides of this mouthpiece. So, that is why the diameter of this jet will be equal to the diameter of the mouthpiece, and this condition is called the running full condition. And in this case, there is again a formula. The formula is same here, but the coefficient of discharge is different here. Formula is Q equal to CdA into under root 2gh, but there is a change in the formula. It is 0.707 here in the case of running full, whereas in the previous case it was 0.5. The formula is same, but the coefficients are different. Now, coming to the notches, the third type of device used to measure the discharge. Now, what exactly is a notch? A notch is an opening in the vertical side of the tank. As you can see in this tank, there is an opening on the side of the tank. It is V in shape here. It is a V notch. So, notch is an opening in the vertical side of the tank such that the free surface of the liquid, now this is the free surface of liquid shown by this arrow, this free surface is below the top edge of the opening. This is the top edge of the opening of the notch. So, notch top level is always above this free surface level. This is a condition. Secondly, this notch can be used to measure the discharge through the tank or an open channel. It may be a tank or maybe through an open channel we can measure the discharge using this notch. Now, what is a weir? The fourth type of device used to measure discharge. It is not just a device, but it is a masonry structure or concrete structure or I can say it's a small dam of very low height. As you can see here also, the water is just flowing over it. So it is built across a river or canal over which the water overflows. This weir can also be used to measure the discharge of water